Hi, I'm Peter Adamson, and you're listening to the History of Philosophy podcast, brought to you with the support of the Philosophy Department at King's College London and the LMU in Munich. Online at www.historyofphilosophy.net. Today's episode, Get to the Point, 14th Century Physics. It's a bit misleading to talk about Aristotelian physics, not because Aristotle was uninterested in physics. To the contrary, he quite literally wrote the book on the subject. Already in late antiquity, and still in the medieval worlds of Islam, Byzantium, and Latin Christianity, his work, the Physics, was the fundamental source for natural philosophy. The word physics comes from the Greek physis, meaning nature. What I mean is rather that, in a way, Aristotle had not one but two physics, one for the terrestrial world and one for the heavens. Down here, in the region where we live, often called the sublunary realm because it is situated below the sphere of the moon, all things are made of four elements: air, earth, fire, and water. They have natural tendencies to move in straight lines, up or down, that is to say, away from or towards the center point of the universe. This is because they are trying to reach what Aristotle calls their natural places. Thus, fire tries to occupy the region just below the sphere of the moon, while Earth tries to work its way towards the center of the cosmos, which is why flames flicker upwards and stones fall downwards. The reason that the four elements do not just sift apart is that they are bound together as composite substances, something that Aristotelians across the ages tended to explain with reference to heavenly movement. It is because the heavens revolve around us that our world is so complex and varied. And revolve around us they do. In the celestial world, things move in perfect circles instead of straight lines. This, according to Aristotle, shows that heavenly bodies are made of a different kind of matter, not the four sublunary elements, but an ungenerated, indestructible fifth element called aether. So distinctive is the nature and physics that governs this realm that Aristotle devoted a separate treatise to it called On the Heavens. For him, the visible planets and fixed stars are seated upon transparent spheres made of the fifth element, which concentrically surround the likewise spherical terrestrial realm. If Aristotle gave the medievals their cosmology, then Ptolemy gave them their astronomy. His system had first been passed on to the Islamic world, something you can still see in the title used for Ptolemy's massively influential treatise, the Almagest. That al at the beginning is just the Arabic definite article. Astronomical treatises of the Islamic world were in turn enormously influential on Latin Christendom, which borrowed everything from terminology, like Zij for an astronomical table, to instruments like the astrolabe. Latin works, like On the Sphere, written in the first half of the 13th century by John of Sacrobosco, offered textbooks for the university students who studied astronomy as part of the quadrivium. As we move into the 14th century, we see that the story of astronomy and cosmology is parallel to and bound up with the story of philosophy. For one thing, we have a similar trend towards use of vernacular languages. Nicole Oresme translated and commented on Aristotle's On the Heavens in French, and a work on the use of the astrolabe was written in English by none other than Geoffrey Chaucer. And, much as nominalism and voluntarism were putting pressure on various long-held Aristotelian presuppositions, so the science of the stars was increasingly subjected to doubt. We've already seen that one key aspect of Aristotle's cosmology, the eternity of the celestial bodies, and hence of the cosmos as a whole, led to intense controversy in the 13th century. Eternalism was widely rejected, even by the hard-line Aristotelians of the Parisian arts faculty. Now in the 14th century, the Aristotelian Ptolemaic worldview received more detailed criticism. In 1364, a Parisian master named Henry of Langenstein argued that the perfect spheres envisioned in that worldview could make sense only as a mathematical model, not as a real physical cosmology. Other authors toyed with revisions to the Aristotelian system, though without necessarily embracing these revisions. Mightn't it be that the Earth rotates under an unmoving heaven instead of the other way around? Could we even tell the difference? We saw in passing that Adam Woדם mentions this hypothesis to illustrate the notion of an apparent property, a cosmic version of the case of trees on a riverbank seeming to move when you are on a boat. John Buridan and Nicole Oresme both discussed the hypothesis too. Buridan decides against it on the grounds that if the Earth were turning, a projectile, like an arrow, fired straight up, should fall some distance away because the ground would turn beneath it during its flight. Oresme disagrees. If someone on a moving boat fires an arrow straight up, the arrow will fall back down onto the same spot in the boat because it will retain its lateral motion while flying. Ultimately, Ockham does stop short of embracing the idea of a turning Earth, but not without first having established it as a serious possibility. Another innovative natural philosopher, active in the 14th century, was Francis of Marchia. Like Ockham, he was a Franciscan who came into conflict with the Pope over the principle of voluntary poverty, and, unlike Ockham, he was ultimately brought to trial to answer for his defiance. Marchia was a pioneer of the impetus theory, which we'll get to shortly. First, I want to mention his views on another matter, namely whether there is in fact another matter, aside from the elements that exist in the terrestrial realm. Was Aristotle right to hold that the celestial bodies are made from a special kind of stuff, indestructible and uniquely suited for permanent circular motion? Here, Marchia offers what you might call an internal critique of Aristotelian physics. On the traditional understanding of Aristotle's view, the most fundamental sort of matter is nothing but pure potentiality. It survives through all change, even change between the elements. Marchia points out that this sort of underlying prime matter is just as indestructible as the heavens. That is, it cannot be generated or annihilated by any natural power. In this sense, matter is the same for the whole created universe, both sublunary and heavenly. It can be admitted that the celestial spheres, with their perfect rotations, are bodies of a different kind than we find here in our earthly realm, but this is due to their different forms, not the matter from which they are made. Where Marchia cast doubt on the radical contrast between celestial and terrestrial physics, others questioned the causal connections that were supposed to obtain between the two realms. This was problematic because taking the idea of celestial influence really seriously in the 1300s was a bit like taking disco culture really seriously in the 1970s. It might lead you to embrace astrology. This was a highly contentious discipline, enthusiastically endorsed by some medievals like Roger Bacon, criticized harshly by others like the author of a work called Errors of the Philosophers. Thomas Bradwardine, too, was fiercely opposed to any suggestion of astrological determinism. A compromise view could be that the heavens do influence things down here, and that astrologers might sometimes be able to discern this. But heavenly influence should not be the sole causal factor determining the events in our lives. At the very least, human free will should also play a part. The stars were also invoked to explain such things as the functioning of magnets, and even the impossibility of creating a void space, since that would imply that there are places where celestial influence cannot reach. Again, though, all of this came under scrutiny in the 14th century. Already the condemnations in Paris back in 1277 had censured the thesis that, if the heavens should stand still, fire would not burn because nature would cease to operate. A couple of generations on, Buridan and Oresme question whether natural processes really depend on causal influences from the heavens. They point to the fact that in the Bible, the prophet Joshua commanded the sun and moon to stand still in the sky, which did not result in a collapse in all natural processes, only a collapse in the enemy's array against the Israeli army. Buridan explains that, without any help from the heavens, the four sublunary elements could simply interact with one another so as to yield indefinite change and mixture. The traditional recipe had celestial influence ensuring that fire keeps turning into air. For Buridan, you can just add water. As Francis of Marchia pointed out in his argument for the commonality of celestial and terrestrial matter, Aristotelian doctrine had it that matter is bare potentiality. Anything made of this matter will occupy space, without any gaps, if you'll pardon the expression, since void is impossible, and be indefinitely divisible. Aristotle understood this last point to mean that, in principle, you can take any continuous body and cut it in half, cut one of the resulting halves in half, cut one of the resulting quarters in half, and so on forever. You might imagine doing this with a cake, taking off ever thinner slices. Aristotle put this conception forward against the atomists who had lived around the time of Socrates, who believed that every body is made up of smallest indivisible parts. You may recall that this is what atom means, uncuttable. Most scholastics agreed with Aristotle about this, albeit with occasional modifications. Duns Scotus, for one, forthrightly rejected atomism, but held that the infinite number of parts that can possibly be isolated in a body are all actually present, not just potentially present. Ockham agrees with Scotus, since he can make no sense of a thing that exists merely potentially. If a whole body is real and it is made of parts, then its parts must be real too. Occam's argument for this illustrates his penchant for transposing metaphysical issues to the propositional level. For him, talk of potential being is just talk of negation plus possibility. Hence, if you say, this body potentially has parts, you can only mean this body has no parts, though it could, which is false since bodies do have parts. The parts are, however, not separated from one another as atoms would be, and in fact they overlap. Half the cake includes 2/4 of the cake as its subparts. Another interesting point made by Scotus, and later by Francis of Marchia, is that the same amount of stuff, what Scotus calls quantity of matter, can be packed into a greater or lesser volume. Here our medieval thinkers are getting at the notion that will later be called mass. A more radical break with Aristotle's theory of matter was contemplated by Occam's teacher Henry of Harclay, as well as Occam's intellectual sparring partner Walter Chatton. Both of them were ready to admit that material things are, after all, made up of atoms, though not of the sort envisioned by ancient atomists. Instead, there would be actual points in a line or a body. Given that, as we just saw, Scotus and Occam accepted that all the parts of a whole are actually present, you might expect them to be happy with this. After all, isn't a line just made up of an infinite number of parts, which are indivisible points? Well, not according to Occam. He argues that an actual point is always the termination of a line, or even nothing apart from the fact of the line's ending. In fact, according to Occam, not even God can create a point existing all by itself. But Harclay and Chatton offered a powerful consideration for the reality of real, discrete points. They ask us to imagine a sphere approaching a plane. We might picture a billiard ball approaching a tabletop, though both the ball and the table would need to be geometrically flawless. In fact, to eliminate the imperfections that would arise in a real case, Chatton asks us to imagine that it is God who creates the situation in all its geometrical perfection. Our medieval atomists now argue that, when the sphere first touches the plane, it will contact it at only a single point. This thought experiment provoked responses from Ockham, Woden, and Buridan. I think the most clever answer is the one given by Woden. He imagines trying to isolate the part of the sphere touching the plane by slicing away upper portions of the sphere. You could start by cutting away the top hemisphere, then take off further layers as you work your way down. If you cut down so far that only the point of contact is left, the sphere will be gone completely. This shows that any constitutive part of the sphere that is really touching the plane must be extended. Further thought experiments, both possible and impossible, played a role in the most famous development of 14th century physics, the theory of impetus. It is associated especially with John Buridan, but first appears in Francis of Marchia. In yet another striking case where theological discussion prompted scientific advance, Marchia takes up the issue while discussing the way that the power of grace is instilled in the sacraments. He draws an analogy between this miraculous case and the mundane fact that a power for motion may be implanted in bodies, as when you throw a projectile like a javelin. Why does the javelin keep moving once it has left the hand of the thrower? For Marchia, the answer lies in what he calls virtus derelicta, or remaining power. Buridan will call it impetus. The theory of impetus is usually seen as a complete departure from Aristotle's theory of motion, perhaps in part because it was already proposed in late antiquity by John Philoponus, who was certainly a stern critic of Aristotelian physics. For Marchia, though, it is just an elucidation of what Aristotle must have meant in the passages of his physics that analyze motion. To Aristotle's mind, there must be something that causes the javelin to carry on moving. Since this cannot be the thrower's hand once the javelin is in mid-flight, he appeals to the air around the javelin. As it hurtles onward, the javelin displaces the air in front of it, and this displaced air is pushed behind the javelin, which gives it an onward shove. If your name is John, history suggests that you will not find this persuasive. Both John Philoponus and John Buridan pointed out the ridiculous consequences of Aristotle's theory. For instance, that people on a boat sailing swiftly down a river would feel wind at their backs and not in their faces. Marchia more respectfully admitted that the medium may play a part in moving the body, while insisting that the remaining power given to the javelin by the thrower also helps to explain its tendency to keep moving until the power is expended. Not everyone was persuaded by the new idea. Ockham, for one, said that it would be amazing if my hand caused some power in the stone by touching it. Impetus theory has clear advantages over Aristotle's account, though. It explains why you can throw rocks further than feathers. Thanks to its size and density, a rock is able to take on a greater impetus. It also shows us why falling objects tend to accelerate, so that a rock dropped off a building will kill you, whereas a rock dropped from 1 inch above your head will merely bruise you. As the rock falls, its impetus constantly builds thanks to its weight. Note that this is not the same as the later scientific concept of inertia. Neither Marchia nor Buridan claim that all moving bodies continue moving by default, slowing or stopping only when impeded. Rather, the idea is that a body can be invested with a power that will make it tend to move, as the attractive power in a magnet moves it towards metal, but this tendency will always be brought to an end. Buridan is still committed to the Aristotelian idea that something must be causing motion whenever motion happens. The heavens are quite literally the exception that proves this rule. There is a passage in Buridan where he speculates that celestial rotation can, in principle, go on forever. In this respect, it is unlike the motion of the sublunary elements, which travel along straight lines and thus must always stop. Earth will stop if it reaches an obstacle, or failing that, its natural place at the center of the cosmos. A heavenly sphere, by contrast, can keep going round and round, as there is no hindrance and no termination of its path. Yet, this is not because the sphere just keeps spinning without any causal influence, the way we would think about a wheel that turns forever so long as it encounters no friction. Rather, the sphere is moved by an externally imposed force, namely the impetus given to it by God or an angel. I know this sounds rather bizarre, but bear with me. We'll see why Buridan invokes an angel here in a future episode. Even in the perfect obstacle-free realm of the stars, then, there is no inertia, only the implanted power Buridan calls impetus. Let's conclude by stepping back from all these theories and asking about the methods that gave rise to them. The frequent appeals to concrete cases, all those thrown projectiles, boats, and falling rocks, may suggest that we are here seeing the rise of observation-based science. But rarely, if ever, do we get the sense that authors like Marchia, Ockham, or Buridan made a special effort to observe such phenomena, never mind measuring them. Like the advances made by the Oxford calculators, these were conceptual breakthroughs, not triumphs of experiment. In fact, 14th century physics often involves thought experiments that could never be conducted in real life. Appeal was made to God's absolute power, that is, the divine capacity to bring about any logically possible state of affairs, like the perfect sphere touching the perfect plane. These discussions of motion, divisibility, matter, and so on make constant reference to Aristotle by way of his greatest commentator Averroes, but my hunch is that a different Muslim thinker helped inspire the use of this sort of thought experiment, Avicenna. His famous flying man argument, much discussed in Latin Christendom, asks us to suppose that God creates a mature human in midair. I covered it in episode 141 of this podcast series. Perhaps medieval science owed as much to Avicenna's startling method of argument as it did to the astronomical tables and astrologers of the Islamic world. That is speculation on my part, but something I can say with total confidence is that Avicenna was vital for a further scientific discipline, medicine. His canon offered an authoritative overview of medicine as a whole, and became the most important source for the Latin Christians alongside the works of the ancient Dr. Galen. We've touched in the past on the relation between medicine and philosophy, in antiquity with Hippocrates and Galen, and in the Islamic world too. Medieval medicine doesn't have a great reputation. Words like leeches and bloodletting leap to mind. But in Latin Christendom too, medicine was a sophisticated science with close links to philosophy. So make an appointment for an interview with Monica Green, whose thorough examination of medieval medicine will put the physical back in the physical sciences. Next time on the History of Philosophy, without any gaps.